Hi, I'm Arianna Renzini, and I'll be telling you about maximum likelihood map making with the LISA detector. This is a project that I coordinated within the LISA Cosmology Working Group with several collaborators listed on the title page. I'm also listing the reference to our PRD publication, so if you're interested, please check it out at the end of this talk. Now, the aim of the project is to write an estimator for gravitational wave background anisotropies on the sky. So we'd like to estimate not just the monopole, but also map the anisotropies of the intensity of the gravitational wave backgrounds on the sky. Now, we might have different types of backgrounds, either sourced by astrophysical or cosmological sources. So if we had a map of an astrophysical background, we could investigate large-scale structure and perhaps even polarization properties of the structure, whereas if we had a map of a cosmological background, we could constrain cosmological models and do some fundamental physics. Now, let me remind you that in the LISA band, first and foremost, we expect to have an incoherent gravitational wave background sourced by the galactic white dwarf binaries, and it will be so loud that it will actually be covering up a lot of very interesting signals. Beyond that, we do expect to have an extragalactic background sourced by stellar mass binaries, and perhaps even we may be able to probe a primordial background, which could be sourced by anything between cosmic strings and phase transitions. Now, while these are very similar backgrounds in nature to those that we probe with LIGO or in general with detectors from Earth, we expect them to behave very differently in the time domain. Specifically, with LIGO, we expect backgrounds to behave as shot noise in the time stream, whereas in LISA, we expect these to be continuous backgrounds, so they're on all the time in the time stream. Now, gravitational wave backgrounds will typically add up incoherently in the time stream, so it's only natural to probe their intensity, discarding all of the phase information that the single gravitational waves may carry. And these signals will be coming from all directions on the sky, so we're naturally interested in studying their anisotropies. And as I've mentioned, we have a variety of different sources contributing in the LISA band, so one way we can differentiate between them is by studying their spectral dependence and picking them out in frequency space. So the structure of the pipeline we've developed is as follows. We start from simulating a gravitational wave background, filtering it through the LISA detector, and estimating the maximum likelihood solution of the map given the data that we've generated. And at the end of the day, we're left with a full study of the anisotropies of the gravitational wave background which we've plugged in. So I'm going to take you through the different steps. So we're going to generate maps of the gravitational wave background, simulate the detector response, and also add in simulated noise. And then I'm going to take you through the maximum likelihood solution we've devised to extract the optimally fitting map to the data with the LISA TDI setup, and also how to estimate the angular power spectrum of the map that we're probing with LISA. So there are different mapping procedures for gravitational wave backgrounds proposed in the literature. Many use different approaches, such as coherent approaches or maybe even radiometer maps. So our approach is most similar to the full sky spherical harmonic decomposition approach used for LIGO data before. However, we work directly in the pixel domain. So the keywords that I associate to our method are we're working in pixel space and in the solar system barycenter. So we're using coordinates where the LISA constellation is not fixed, which allows us to have a generalized pointing solution on the SSB sky. We're trying to map extended sources, so this is very different from localizing point sources on the sky, which you might want to do when you're localizing merger events, for example. And we're able to do this by using long integration time. So we're going to be using the full time of flight of the LISA constellation to our advantage. So the spirit is utterly similar to the approach used in work I've done with my supervisor, Carlo Contaldi, throughout my PhD. So I'm leaving here the links to those archive projects so that you may go and check them out. So the maximum likelihood mapping approach is utterly simple. We write down the likelihood of our intensity map given the data D, which is decomposed into a pure signal and pure noise component, and it's written down as a Gaussian likelihood in equation 2. So here in equation 2, you can recognize the covariance C, which again is decomposed in a pure signal component, which contains the intensity I of the gravitational wave background, which is being filtered by the response of the detector A, plus the noise covariance. So the way that we go about it is we extract the optimal map estimate I tilde by maximizing the likelihood L with respect to I. So this method works as we assume that the data D is a mean zero Gaussian variate, and in this case it is also an optimally fitting solution. So this is quite different from what we did for LIGO or for ground-based detectors in general, where we assume that the cross-correlation of the data streams from the two different detectors are Gaussian variables with average just consisting of just the cross-correlation of the signal components. And we use a residual to construct the maximum likelihood solution. For LISA, the approach is very different. We're actually just assuming that the data itself is a mean zero Gaussian variable. So on one hand, it's more simple, but on the other, it allows us to take into account the fully correlated setup that we see with the LISA constellation. So this will become more clear in a minute. So as we go about minimizing the chi-square, we obtain the optimal solution in equation 4, which is an utterly standard equation. It's the Bond-Jaffe-Knox solution already used for CMB mapping. So here you can recognize the Fisher matrix F in pixel space, so P and P prime are pixel indices, and it's being inverted and applied to the gradient term in the trace. And this, in turn, gives us the optimal estimate for the map I tilde in pixel space P. So as some of you may already have recognized, this is not a closed-form solution. We actually need to iterate to obtain the optimally converged solution I. So what we do is we start with an initial guess I0, which we plug into the covariance C, which appears in various terms in the equations in this very busy slide here. And then we iterate until convergence is reached. So as I mentioned before, the different detectors that we're considering here for LISA are actually just different time delay interferometry configurations that we're arranging to obtain a measurement of the gravitational wave background. So very briefly, the three LISA satellites that compose the LISA constellation will be measuring the gravitational waves by linking together the different links that compose the LISA setup, and there's different ways that you can compose these links to obtain an optimal measurement of gravitational waves. So different types of configurations will give you different measurements. Specifically, we're using the TDI 1.5 configuration, which is presented on the right-hand side of this slide. So as you can see, we're assuming the TDI channel X to be the interference between the path in red and the path in blue. This is specifically studied to minimize the noise present in the readout of TDI channel X. So you can make similar measurements centered about satellite 2 and satellite 3, and you get the XYZ TDI channels 1.5, which correspond to 3 correlated detectors of gravitational waves. Now, let me tell you a little bit about how we construct the data that we feed into our pipeline. Now, the signal component of the data is simply constructed by using the theoretical strain measured by the TDI configuration, which is written down as in equation 5. So here you can recognize the strain the gravitational wave strain H decomposed into plus and cross polarization components, which is being picked up by the detector, so in this case by the TDIs X, Y, and Z labeled by I, with different polarization response functions R plus and R cross. So these different functions will modulate how the inclination and the position of the detectors react to the differently polarized gravitational waves. Now, the cross-correlation of the signals from 2 channels can be written down as in equation 6, which gives us the cross-correlation signal matrix, capital S. Now, effectively, this will actually give us the intensity of gravitational waves, which is just what we're after. So, as you can see, the correlation matrix S is the integral over the whole sky of the correlation response function, the quadratic correlated response function A, which is filtering the intensity I on the whole sky. So note how A is actually a 3x3 TDI matrix given by the outer product of the response function matrix by the response function vectors R and R star. So what we effectively do is we generate a map for the intensity of gravitational waves I, we plug it into equation 6, and we get a set of correlated TDI data for a single moment in time. And then we iterate throughout different moments in time and get a whole data set for the LISA TDI configuration. Now, the noise portion is a little bit trickier. So what we do is we actually need to consider the noise to be correlated for the 3 different channels. So what we do is we generate a correlated noise vector Ni, where I labels again X, Y, and Z, as a realization of the theoretical cross-power spectrum N. So effectively what we do is actually we generate a random 3-vector ABC, so a vector in uncorrelated noise space, and then we rotate into correlated space by using the eigenmatrix of the noise power spectrum and the theoretical power spectrum N. And then we obtain a realization of this cross power spectrum by taking the outer product of the noise, the correlated noise vector nx and y and z. Now, there are two dependencies for the LISA TDI configurations, which we are going to be using to our advantage to make high resolution maps of the gravitational wave background. So the first is to study what the time dependence looks like for the TDI channels. And effectively, what we need to understand is how the LISA constellation moves in the solar system barycenter frame. So effectively, the spacecraft positions in the SSB are going to be time-dependent vectors, and what we do is we generate the data portion for segments of 48 hours, throughout which we assume that the position of these vectors is constant. So for example, we can look at an instantaneous response of the quadratic X signal. So this is the autocorrelated response of the X channel, and it looks like so. So it has the hot direction and then the two quiet directions off of the solar system, off of the LISA plane. So you can recognize the 30-degree angle and the 60-degree angle. Now, if I look at what this looks like as a function of time, we see that as LISA moves around in the SSB, the hot direction is scanning the sky, and the cold directions are also moving around. So this is giving us an idea of how LISA responds differently as a function of scanned direction. Now, a similar game can be played also in frequency space. So effectively, the response function A for TDI X, Y, and Z will look very different on the sky depending on frequency. And this is because of the coupling between the frequency and the direction on the sky. So as we move up in the frequency range for LISA, we see that we get a very different response on the sky. So two things happen. On one hand, we get a quieter response, so the detector becomes less and less sensitive to gravitational waves at higher and higher frequencies. But on the other hand, we gain in resolution. It's going to be the interplay between these two characteristics that actually makes or breaks our resolution on the sky. Now, for the final part of the talk, and possibly the most interesting, let me show you the results that we've obtained simulating data for the TDI 1.5 channels X, Y, and Z. In different cases. So let's start from the low noise case. So we're considering the input noise to be much, much smaller than the signal. So it's sort of a vanilla test study case. And specifically, we're also assuming the arm length L to be constant throughout. So on the left-hand side, you can see our input map. So it's an independent L squared CL flat realization for I. And it's like so. It's a very finely distributed Gaussian realization on the sky. And on the right-hand side, you can see what our extracted maximum likelihood solution maps look like as a function of Fmax. So here, Fmax is the frequency that I cut off my integral when I'm realizing the output map. So the Fmax will give you an idea of what the resolution is going to look like if I have a signal with that type of distribution on the sky, which is loud at that particular frequency. So you can see that if I have a signal which is on a very high frequency, so 0.1 hertz, I have a pretty good resolution, so the input and output maps look very similar, and you can imagine matching them and figuring out a very small residual. Whereas if I have a signal which is only on lower frequencies, so say 10 to minus 2 hertz, the signal is immediately watered down and I lose a lot in resolution right away. So you can tell that the hot and cold spots are roughly in the right places, but the resolution is lost very quickly. Now, a better way of quantifying this is actually just looking at the CL reconstruction. So we're looking at the angular power spectrum of a simulation run of these maps. So I run sets of 50 of these maps for different Fmax integrals, and I test how well I reconstruct my input and output CLs. So you can see that up to a maximum frequency of 10 to minus 1 hertz, I am able to obtain a maximum resolution L around 15, 16. So L max 15, 16 is actually pretty high, but I lose that resolution right away as I go to lower and lower frequencies. So you can imagine that a signal which will be on at, say, 10 to minus 3 hertz will only be able to be resolved as a very large blob around, L max 3 or L max 4. You can translate this into a transfer function. So looking at the right-hand side of this slide, you can see that depending on what Fmax you have, you get a transfer function close to 1 up until up to a certain Lmax, and this will give you roughly the angular resolution that you can expect to have at that particular frequency. So note that there is aliasing and leakage in this procedure, and it's related to the conditioning of the Fisher matrix. Now, this is quite a complicated argument, so we can talk about this more perhaps in the comments. Now, I've also tried reconstructing a map at a very low SNR, so an SNR of 0.6, to see how well we could do if we actually had a signal which is also buried in the noise. And we're still integrating to a very high Fmax, so we're integrating in the frequency range between 10 to minus 4 and 10 to minus 1 hertz. However, our signal is buried beneath the noise. So you can see that high noise has a very similar effect to a low frequency cutoff. So the higher L modes are dominated by the noise, and so a very strong conditioning is required to actually extract the map. We're using, in fact, an SVD approach to extract the map, and we're discarding something around 98% of the eigenvalues to actually get out this map. You can see that the hot and cold spots are roughly in the right place, but the signal's been massively watered down, and we've lost all of the resolution that we could have gained at that high frequency. Now, finally, let me just show you the study that we did, but regarding reconstructing a Milky Way signal, so a galactic binary signal distributed on the sky as the Milky Way ring, which appears like the top left panel in the solar system barycenter. And again, we tried to play with this in two different setups. So the top row is a high signal-to-noise case, so we basically have no noise, but again, the signal from the binaries is only on at very low frequencies, and you can see that the very best resolution that you can have is still quite low, and you can see this in the top right panel here on the slide. And then finally, we tried a sort of very realistic case of a medium SNR signal, which is on at galactic binary frequency, so between 10 to minus 4 and 5 times 10 to minus 3 hertz, and effectively the output map that we're able to achieve is a massive blob on the right hemisphere of the sky, which again is in the correct place. And let me also reassure you that the monopole estimate is correct. However, our angular resolution is completely lost because the signal is not only at low frequency, but it's also dominated by noise in the higher portion of the frequency space. So we're obviously still working on this. There's a long way to go. We'd like to do some more in-depth studies of the Fisher matrix, which will set and refine some of that resolution that I've been talking to you before. We'd like to add realistic noise and signals and really test the limits of map making with LISA. And we'll also be taking this to the LDC data and see what we can figure out. So thank you very much.